Hello. I'll be talking about two interesting bugs that I've tried to write an exploit for at least. If you've seen my Ruxcon talk, the first sort of half is quite similar to that, though I've tried to explain things better than that, and my slides are a lot nicer because I ripped off this style from Google. And there's two interesting bugs, the ReducedRight bug, which we'll talk about for the vast majority, and then this IDB key range use after free, and I'll talk about my approach to that and the Firefox bugs that I use. So about me, this is all you really need to know about me. Is I had quite a few positions. I had some nice ones like this, but I chose the chin shelf because it's a fucking classic. All right, it's a fucking classic. All right, so the ReducedRight vulnerability. As I said in my first thing, I actually didn't know what ReducedRight did when I first wrote this exploit. Actually, I don't even know what IDB key range actually does. You don't really need to know about the actual what functions do, just the underlying mechanics of them, right? So ReducedRight is kind of like if you know what map reduce is. So reduce is like that in the sense that if you have an array and you want to, let's say, sum up all the values there, you do reduce on that where you pass a function to it, and it calls that function on every single one of the items inside the array, and then so it calls it on the current item, and it also passes the last return value from the time that function was called before. So your summation thing is like current plus the return value of the last one, and it just goes along, and then your return value is that. So the ReducedRight is the same as reduce, but instead of starting left to right, it starts right to left. So this particular bug affects all versions of Firefox up to 4.0. It's found by Chris Rolfe. I also stole his the font from him, from his nice Knackle talk. So I stole not only his bug, but his font. And there's three pretty public exploits for that. And I first learned about this bug because ATEL was talking about how they wrote this exploit that used an info leak, and it was not only an info leak, but also like code execution. I was like, oh, that sounds really interesting. I'd like to write that exploit. And I looked at all the public stuff, and it was pretty shit. There was only one using the info leak properly. The immunity one did use it, but they heap sprayed to do that, and you don't even need to do that, as we'll see later on. So I thought it's an awesome vulnerability and deserves better than that. And but before we actually jump into the vulnerability, we need to talk about JavaScript internals, because I'll be saying the word JS value about 1 billion times during this entire talk. So SpiderMonkey represents JavaScript items as these JS vals. And essentially what they are is these 64-bit data structures where you have a tag which denotes what kind of item it is, whether it's an integer or a boolean or an object, and then the actual value itself. And whether that value is complex in the sense where an integer isn't complex, it's just like a number, so you can have the tag and then the number, compared to an object where you have the tag that says it's an object, and then a pointer to a structure, which is a JS object, which describes that object in a much more complex fashion, like where it actually is there. So they're the bits. So if you do this in JavaScript, you create a new array and you put these values in there. This is the JavaScript array that is created. As you can see here, we put elite in, and we have this very elite number, and we got an object. We got boolean. I probably should have chosen true instead of false because you have a 1 there then. And one interesting thing here is that you have doubles, and because doubles are 64-bit objects, you need the full 64 bits. It means you can't have a tag. So the double here is represented as a big crazy fucking hex number. And if you ask JavaScript or for SpiderMonkey to go and interpret this 64-bit area and say this is a JS val, tell me what it is. If it can't find a tag, if it can't find like any of these FFs, it'll go, oh, it's a double, and it'll just treat it like a double and return it to you as a double. And this is because you can't actually make those FFFs at the top using any kind of floating point math for whatever fucking reason. It's just, that's why they chose it. I didn't bother to find out why, just maths. Someone can probably tell you who's smarter than me. Yeah, so this is why that was particularly chosen as a tag, because if you could do double maths to make that, then you can make fake strings and fake objects, and that's obviously going to be a problem because now you're making fake JavaScript objects out of doubles, and that's crazy. By the way, please interrupt me if you have any questions or anything like that. So JavaScript string, so this is what a string, the tag and then the actual pointer. So the pointer points to this JS string object, and all it is a length field that also contains flags denoting what kind of string it is. because there's actually multiple types of strings in JavaScript. For instance, there's like rope strings. So if you ever go like ABC plus CBD, it creates a rope string, which is like, instead of putting them together in a single line, it actually just creates this pointer that goes like, oh, this string is actually ABC plus CBD. Anyway, so this is, it has the type there, and then the actual pointer to where the words are. And then we have a JS object. So any non-native JavaScript object is represented as this. I say non-native in the sense that it's not a number or a boolean or something that's very simple. So if you create a DateTime object, you'll have you'll create a JS object in that, and you have the slots array inside JS objects, which is just literally an internal array which has a number of JS values, which are these back to these simple native types. So back to this date and time example I'm talking about. If you create a date and time, you obviously have year, date, and things like that, and they're just stored in the slots array as these numbers. And that's actually what denotes a DateTime object. And a map is kind of like, so they have a map and a class pointer at the top, and they're kind of like vtables, but for this particular object. And we don't need to know much about them other than they point to inside JS. And the slots array is actually inline in the GC heap up until a certain size. So when you create most JavaScript objects, they are stored in the GC heap. But when they grow above a certain size, like if you have an array, and like that array we saw previously, if you grow that to above, I think 16 is the default size that you probably can't even change, but it's the size, it gets reallocated in the JE-malloc heap. The JE-malloc heap is this more generic heap where they have like strings, DOM objects, XML, SVG, anything like that gets in there. But importantly, JS objects are all in the GC heap. And also I really fuck up when I say it a lot, and I say like the JE heap and things like that, so if you ever hear me saying that, JC heap, and if I ever say JE heap or GE heap or JE-malloc, I'm probably talking about the other one. That just I just confuse the shit out of myself then as well. So here's the bug, right? It's in this array extra function. And we have this unsigned length field here, and we call getLength property on there, and all that does is takes whatever you've set the length to the array, and it puts that in this variable. And it doesn't do any checking there. So if you go like new array and you go array.length is equal to 1 billion, it'll just put 1 billion into length. Because the actual JavaScript array length isn't actually the length is capacity, which is different, and that's how they know how big they should grow it some more. So length is just a fucking number essentially. And we go down here, and this is for, remember when I was talking about the reduce thing, so we're going to go down, we start at 0 obviously and end as a length, but when we're doing this particular reduce right, we're starting right to left, so we start at the end. So start is equal to length minus 1, start is equal to, end is equal to the minus 1, and then we go through this loop starting at wherever I is set, and we call get element with I, which is our length thing, and there's been no checks on that size at all. And get element for that index, it takes a double, which is inherently a signed thing. So if we can pass in quite a large number, which is then interpreted as a negative number. Firstly, this JS assert, which would have caught our vulnerability, doesn't ever happen in normal Firefox. This is only with debug modes. So if you ever like auditing Firefox and you see, oh no, this JS assert would have caught my vulnerability. It doesn't, it's fine, it's not in the real Firefox. So our index is checked against the dense array capacity, which is at the actual size, and we'd be doing new array, that's 8. So our very large number, which is actually now interpreted as a negative number, is then obviously smaller than that, because it's probably like minus something, and then it's then cast to an unsigned int, and then it literally just gets that. And what that boils down to is that we have the slots array, this internal array, which denotes the object, we can control the index. And that's pretty good. And so I took this description from Chris, did a much more coherent rundown of the vulnerability. So if you want to have a good link, click on that link. Though I don't know if I put slides online, so just click on it with your mind. Yeah, click on a link that I send you. That'll end up well. So to trigger the bug very easily is just this. You create a new array, you set the length to a very large number, which is also signed math as a negative number, and you call ReducedRight on it with your function, and this alerts. And the one line of assembly where it boils down to when I was talking about the slots array, EX here is the slots array pointer, and we have our ECX, which is our length thing, and you can see it's also the FFFB. We put in the C, but it's length -1, and multiply them together, and now we're actually pointing behind where the slots array starts. So we've now referenced outside of the JavaScript object or behind where the actual array is meant to be, and that's obviously a bad thing. We can go backwards, we can go forwards, we can go anywhere. And what's good about this is that because we're now referencing outside of it, we can get anything from an offset from the slots array interpreted as a JS value, and that's very interesting when we came back to what a double is, because if it doesn't find a tag, it goes, hey, this is just a double, and returns that value straight to us, which is very useful for info leaking. So we can specify a negative index. If we look again at our JavaScript object, I've highlighted here in red as these 2 pointers. This is the map and the class pointer. And so you have to excuse me, my throat is kind of sore after yelling at people in bars the last couple of nights. This is the same object, and you can see here that these 2 pointers are well within Moz.js. So all we need to do is set a negative index and leak backwards, and we'll have these 2 pointers returned to us as a double, but they obviously contain this data. So that's literally the same code I showed you before, but instead of doing a load on the current thing, I have some sanity checking up here, but it literally just goes double to bytes, which is just this really fucking crazy function that Mark wrote, which turns a double into the actual byte value, and it's just ugly as hell, and then bytes along just some things, but it literally just takes that bytes and returns where a pointer to inside Moz.js is. So we have this pointer now to somewhere inside Moz.js. And the easiest thing to do is go, all right, so it's like Firefox 4, or we can start fingerprinting all the different other versions there and go, all right, so we have this pointer inside there, we'll just take the offset to the base of the pointer, and now we know where Moz.js is actually loaded at. But to do that, we have to do a fingerprint accurately Firefox, and we have to get offsets for every single Moz.js DLL, and that's kind of a pain in the ass. So I thought, why not over-engineer this thing a lot and try and turn this into an arbitrary leak instead of just a leaking inside Moz.js. And what we can do then, if we can turn it into an arbitrary leak, we can just walk backwards until we find the PE header and go, hey, this is actually now the base of Moz.js. Instead of, especially since their DLLs are mapped to 64K objects, you only have to leak a couple of times to actually to do this, not like 4 bytes at a time or something. So we need to create, we need to turn this into an arbitrary leak. So why don't we create a fake string of some sort? And if you remember back when I was saying the strings, all you do is have like a size and a pointer, and this pointer can point to wherever it wants. And so from there we can walk backwards. But to do this, we need to make our own string JS value. And most people did this kind of thing, like the immunity one did the info leak by heap spraying, and then they knew where the stuff was in memory because it's like an OC, which had this fake string, and then they info leak like that. So that's kind of lame doing it like heap spraying, because I don't really like heap spraying. I'm apparently not lame, though I am. I'm going to talk a little bit about heap feng shui. Ooh, that's probably fine. Yep. So heap feng shui is a term Soderov came up with, where it's creating this it's creating this heap layout that is good for our chi, is having laid out and everything in a pleasing manner to us, right? And our end goal is there's something like this picture here where we have this slots array, which is where the pointer is, and we want to be referencing outside that, and we want to go and reference some of our attacker controlled data, which will contain our fake strings. And so, but we need to make the heap layout look something like that. And then once we can do that, we can create our own fake JS values, because it's our own arbitrary data, so we can make this, it's literally just a tag and a pointer. So we just need to line everything up. So I'm just going to go through this at a very high level. We're back in this J.E. Malik heap thing. And as I said before, it manages like strings, DOM, and a whole bunch of other, it's just the more generic kind of heap from the specialized JavaScript heap. And it's controlled by a data structure called an arena, which manages chunks, which are these 1 megabyte things, which goes down to runs. And a run is really what we're interested here. And run is like, a bit of memory that services a particular size. And these sizes are rounded up to the closest 16-byte boundary. And so when you allocate something, let's say 34, it goes to the arena and says, hey, is there a run for OX 30 to not 40 inclusive stuff? And if there is one, it'll return a block from that run and go, here's your bit of memory. And if it doesn't have one, it'll create a new run, and then every allocation for that particular size will come from the exact same run. And what you should take away from that is that when you allocate things of the same size or similar sizes within the 16K leeway, they're all going to come from adjacent or similar memory. So the TLDR of this is, if you allocate a bunch of things, after a while they're going to be sequentially in memory. But the problem is that people have been browsing like fucking Sydney Morning Herald and like a bunch of like crazy websites doing all this JavaScript stuff, and your browser's in like this weird state when it first starts going, and that means there's all these holes in the heap, and there's you don't really know what's going on there. And so what you need to do is defragment it, which is another term for Solarop called, and that is essentially filling in these holes. So firstly, you want to cause like a garbage collect, which gets everything sort of taken away, and then you start allocating things that fill in all these extra holes. So after a little while, once these holes are filled in, potentially, hopefully, you can just allocate enough to create a new run, and that new run will just have all your data in there, assuming there isn't time enough for other things to be allocated in there. And those be filled up, and you'll have just your data one after another. So what are we talking about? So we can make these fake JS vals really easily by just allocating stuff one after another, and it's literally that simple. And what's good about this particular vulnerability is that the penalty for failure is really low. So if we don't have this, if we, instead of having our attacker-controlled data, Sydney Morning Herald put some fucking Lady Gaga, article that just happens to be the same size, and it slots in here, and we're trying to trigger our vulnerability, and we reference outside it into what we think is our attacker-controlled data, and we access it. Because we're going to be trying to make a fake string, and it's not going to treat it as a string unless it finds this tag, then it's just going to go, oh, it's a double, and returns it to us as a double. So we don't crash, we don't break, nothing actually happens. We just get a double back instead of a string. And we go, oh, well, we can just fucking try again. So we redo the whole heap thing and go. And so the chances for crashing is very low. We'd have to actually have these very particular bytes here. Secondly, if, let's say, these bytes were there, chances are it's actually going to be a legitimate object, because it's unlikely this stuff is going to be there and not be an object. And if an object is returned or a string is going to be returned, then they're legitimate objects and strings, and therefore they're not going to crash when we try and access them. So the penalty for failure, which is why I was very laissez-faire about this whole heap grooming part of it, the penalty for failure was like basically nothing. Like I can sit there and I can spam the shit out of F5, and I'm not going to crash my thing, even though I'm interrupting my heap grooming and I'm leaving it in this indeterminate state. Also, we can't fall off the page if we look backwards. So, we have a choice. We're referencing from outside of our slots array whether we're going to jump over our slots array or we're going to go backwards into whatever is there. If we go like to higher parts of memory, we have the chance that we're the last item on a page, and therefore we're going to be referencing outside of something that's been allocated. But generally, there's heap metadata at the start of a page. So if we reference backwards, we're going to hit in heap metadata and not actually hitting outside of unmapped memory. So, so far, at least, I've never had a crash like that by going backwards. I don't think it is possible. So, the actual how to info leak. This is the dot points of how I do it. I create a new array. I leak the slots pointer for that item, which now means I know where that JS object is in memory. I know where there's a couple of values that are there that I can set. When I put in the first slot, our size and order with our flags and move slightly over in the top 32 bits and then the address in the second 32 bits. So I've created our fake object we're pointing to. I defragment the heap I chose 512 just because because it's large enough to not be particularly well used. If I chose something that's much smaller, then there's going to be much smaller allocations than 512. Really, I should probably have chosen something larger, maybe like the highest for the J malloc thing. But as I said, the penalty for failure was so low, and I did get 100% reliability with this. So you defragment the heap with these fake JS string values, and you just keep doing that And then after you've known that you've created a new run, that you've created enough of these things to have a very good idea that your data is going to be sequentially in memory, you then reallocate your slots array, which means that it goes from the GC heap over to the JE malloc heap. And then you trigger the bug. And why I put these values in this first slot the very first time is that because I know where these values are because I've leaked the slots pointer and I put stuff in there, but I reallocate it later on. And this is because these values aren't nulled out when this particular array grows too large and grows into the JE malloc heap. And that means I know where they are in memory. I should really have just used 2 arrays and leaked where one is, and then gone, I know this is memory and I can point to that. But I decided to do it with 1 array because I don't know why. I didn't think of using 2. I was just like, sometimes when you're writing exploits, you're just like retarded sometimes. And it's good to step back and think about these things. And you only really realize that when you write a presentation about it and go, why the hell did I use 1 array and do the hard thing about it? Anyway. So actually what this looks like in JavaScript is, I got my 2 arrays and I've leaked, in this ... I've leaked the thing. And this is me creating an unsigned int uint32 array here for every single one of these parts of the for loop. Then at a particular, I chose 400 for whatever fucking reason. I reallocate my array, and I reallocate it by growing it. And I put in my very first part of the array the fixed address size and the actual address. And the rest of it I just put with nonsense numbers, just A's, because that's what we do in security. And yeah, it's 512 because uints and things. So that allowed me to make a function called leak, where I can just go address size, and it goes and leaks that out for me and creates this fake string and does all this magic and returns the data to me. And so leak size. And then now we can get the base address, which is back what we were talking about before. I leaked that very slots, that very first thing, which we could have just minus an offset for, but we didn't. And I walk back 64K every time until I find the MZ header at the head of the PE. And that's when I know I've found the base. Any address. Because you just create a string that just, the string is located here and it's this size, and it just goes there and does it. And sort of interprets that. Then you'll crash. You'll crash. Yeah. Yeah, so if I want one past the MZ header, I'm probably going to be in unmapped memory, and then it'll fall over for sure. And someone asked when I first gave this talk about why I chose 40 in this loop. I just put it there the first time and it found the MZ header, so I was... job done. Yeah, don't change it, it's the magic 40. So, pop and calcs, same deal, but instead of making a string to go and point somewhere else, you make a fake object. And everyone else's exploits used the set element function, which is called whenever you get an object, which is actually our fake value, and it's been set to something. So this is the trigger part of my exploit. There could have been easier paths, but basically what this gives you is a call pointer that you can control, because we can control EDI, and it's moved into EX. EX is then tested to see if it's null. If it's null, it's set with a default property, I think. Yeah, and then it's calls a pointer, which is obviously a winner because we have an arbitrary leak. So current is our fake object, which is our thing. It's returned to the current thing. And so we're calling set element on that because we're setting 0 element with something that we can control. And CC is some other data that is specific to the starting off the ROP chain. And also this throw 1 is something that only one of the other public exploits managed to figure out, is that when you set the length thing, because it's meant to happen length times, if you don't throw 1, it'll just happen like 4 billion times. So you have to throw 1. So I think only one other person figured that out. other than Chris Rolfe, which was strange. That's pretty loud. So yeah, this call EAX will kick off this ROP chain, and it's not particularly novel other than I had to do it over 2 pivot points. I actually got my students to do it for one of their classes, and most of them, it took how long? A couple of hours. Yeah, I mean, like everyone, you know, the pivot was the hardest part because it's over these 2 different gadgets, and you had to figure out. Like I tried to like help them out a bit, but like it was this double pivot, which was kind of interesting. Made a stack reader writable, you know, popped some calcs. I used Mono.py, which was okay-ish. Like it had some good parts. It gave me a good vague start. But don't ever look at the source code for Mono.py. It is the scariest fucking thing you've ever seen. They don't. They need some new lines between everything because it's like Python, but there's no white space in between all the lines. Yeah, I did it on Christmas Day. That's what I did on Christmas. There's basically no process repair for this other than when you do your stack pivot, you have to save your ESP value, and then once you've popped your calcs and your shell codes run, you need to then restore ESP so it can then continue on like normal. And normally when you do something like this, you don't just like return straight to that first function. You might have to return a couple of places up the stack, and that occasionally means like setting an error flag into a register, which is reasonably easy because you control the registers, right? And for me, it was just zoring out some stuff or like nulling out some registers and then returning up the stack. Yeah, I had a lot of trouble running this multiple times in the same browsing session, and this only happened when I run all my shell code, and I comment out or I knock out the last 2 bytes, which is actually call winexec. Then I'll get some weird heap corruption going on, but I seem to have fixed that in the meantime when I was at my hotel this afternoon. So hopefully that's fine. Hopefully that's fine. Yeah, so there's some other people. I won't even talk about their stuff other than, yeah. Everyone else heap sprayed. That's the end. So here's a demo. If there's also any questions, please shout them out. So I had a much more interesting demo in the Ruxcon thing because I could sit there and I could talk through things and I thought there'd be a smaller kind of group of people. But I didn't want to do it at Ruxcon when it's first been recorded because I was making fun of someone. Yeah, here's me popping a bunch of calcs, and this is obviously not me refreshing the process and things like that. This is almost be really. Here's my hubris, and it's mashing F5. So yeah, this is what you kind of want. You don't want like heap spraying bullshit where you have like a fucking 3 gigabyte Firefox because it's 76 megabytes, right? This is not heap spraying. This is how you should be doing things. And so that was why it was kind of disappointing. All the other exploits for this particular bug because it was an awesome bug. And this is So any questions so far?
All right. So from the beginning when you start looking at the bug and the public works to get to kind of simple libraries and implementation.
Yeah, of course. Well, it is a very interesting bug.
Yeah, it's the device change.
Yeah.
Cut off. It's not a good environment to use the lapel mic in this room. Okay. I'm going to just yell loudly. Yeah, you can use the letter turn 1.
Just do as you're told.
Try to power.
Right, so 5 days, that's like without sleep?
No. I did it over like quite a little while. Because it wasn't particularly like difficult. Like most of the stuff that was there is just like they're
easy wins because you have like, this nice call when you can make an object, and the fact that you could, when you did lose with the heap feng shui stuff, it wasn't like a big problem for you. So you can just continue on and just retry it again. Literally at the bottom of my leak thing, when it does fail, it just calls the leak again until it leaks the right size and you actually leak that stuff. So because of that, it was actually a very easy exploit, at least in my opinion, which is why I was also sad that no one actually had gone and really understood the vulnerability, because when you're looking at the other exploits, no one had really understood what you can do with this and stuff.
Yeah, we can't heap and then
Heap everything and do that. So I came...
You also should have been pivoting.
Yeah, right.
Double pivot, I think you did.
So I came, you know, I've written that exploit, and I was feeling pretty awesome. I've written some other things, and they were like fucking like great. I was sitting there, like, you know, flexing in front of the mirror. I was feeling like muscle nerd and shit like that. I was like, I'll take it. Sorry.
the arm wrestle came.
Then the arm wrestle came later. Arm wrestle muscle nerd, and it did not end well. And I was like, oh yeah, I'm pretty awesome. I read about this other exploit. It's used after free, and it's IDB key range object. And Movement did this really great write about how they exploited it. They did this like 3 heaps break thing, and I was like, wow, it's really sloppy. So it was. Look, I at least started doing 1 heap spray, not 3. 3 was fucking crazy. And so I was like, oh man, these fucking Frenchies have no shit about I'll just still do this over the weekend, you know. And I couldn't. I ended up knocking out the exploit. So this half of my talk is about my failure to try and do that, and all the things I tried to do, and it's not good. Well, hopefully you'll still find this interesting. Yeah. It's off now.
Why don't you use this one here?
What one? I'll be like Jerry Springer. I'll do that. So here's my amended talk title. Yeah, why you should do your research before writing your fucking 100% exploitation. Well, look, I couldn't do it without heap spraying, which is what my goal was. Like being able to do it without heap spraying, a nice like straight away kind of thing. Like, have you ever seen like a heap spray exploit work? It's just like, you know, the browser sits there for ages. Every time my browser like takes too long, I just want to like, close it in case it's heap spraying me. And then I'm like, oh, it's just Firefox. Anyway, so here's the actual bug. Well, here's where you trigger the bug. It's in the IDB key range class I mentioned before, and you trigger it down here. So this IDB key range only thing creates the IDB key range we call .lower now, which calls this function. The first time this function is called, it does this internal part where it caches the value for this and caches the lower value. And it calls this hash define, which is kind of cryptic. I'm sort of like what covers that. And what this does is this adds it to the cycle collector, which is a specific type of garbage collector for objects that can have cyclical references to each other. And that's the problem for most garbage collectors because they can't collect cyclical objects. And so all it does is it adds that particular this object to the cycle collector, and it's never released. So when this thing is cleaned up, it still has its reference in the cycle collector. So the bug fix is particularly illustrative of this, because this is how they fix it essentially. It is rooted, like we have added it to the cycle collector. First thing we remove the cycle collector, and we null out and we void the rest of these values. So that's the best way to describe this. These particular vulnerabilities. So I didn't know what the cycle collector was, and we didn't write about it very much, or at all, I don't think, in their particular blog post. And there's all these really dry academic papers about it. You can ask Anthrax, the skinniest guy here, he writes like JavaScript stuff, and he'll probably tell you about it for hours. But essentially, it's like if you have 2 objects like this, where object 1 is referencing object 2 and object 2 is referencing number 1. Their reference count's never going to reach 0 because they both reference each other, even though no one else references them. The garbage collector doesn't know that, can't step in, because waiting for those things to hit 0 to then go clean themselves up. So the Mozilla devs had this thing, the cycle collector, where classes can sort of volunteer, go, hey, I might have a cyclical reference or have that possibility, and they can volunteer their classes to join that, and then they hash define a bunch of functions, and they add in like things we have to traverse and trace these particular particular objects, and then when they do have a cycle, they can then unlink them. So we'll talk about some of the helpers. There are other helpers and there are other functions, but these are particularly pertinent to what we're talking about here. So you have these pointers that are inside this object, right? And you as the Mozilla developer sort of know which kind of suspicious pointers you might have, or ones might have this cyclical reference. And you can go, hey, you put your hand up and you release this, and this might have, there might be a possibility of a cyclical reference. And trace happens reasonably often. It's on a timer, and also every time a garbage collect happens, you can force a trace, and it's called over and it looks at some of these pointers. And then it collects these suspicious pointers, and every so often, and this thing's on a timer, I was not able to find any way to actually force like a cyclical garbage collection to happen. Like the verse is called, and this is where it actually creates like a map or a graph of these objects. And if the graph finds a cycle, and then the reference counts can be, reference counts can be, what's the word? A couple of other out.
Together, decremented?
Yeah, so if each one only is like, if they're only referencing each other and no one else is referencing them, just so the reference counts here, then it goes, hey, there's actually a cyclical reference there. And it's called, and then you call unlink on these. Unlink doesn't actually garbage collect them. All it does is it breaks this cycle and it goes there and it actually, most unlinked things kind of look like this. It basically nulls out various pointers, reduces the reference counts, and then the actual real garbage collector comes in and steps in there and actually cleans up these things later on. So all it does is break links essentially.
It's voluntary, right?
It's voluntary, so you have to create these functions to be able to traverse your objects, because the garbage collector can't, or the cycle collector can't know how to walk your object. So this is where the traverse and trace comes in. Like, you have to write that as a developer and go, here's all my stuff. I show one of the functions. Trace. So what we have to work with here is I have a key range object. It's free. It's this particular size, 38, hex 38. It's not a JS object, so it's in this. It's in the JE now. So when you use up free, the whole idea is like, well, the whole point is like, what do we replace this stale with free? You know, what can we replace it with? And it's not like a typical use up free. Well, there isn't really a typical use up free, but the ones that I'm most particularly familiar with is where you can create like an object in JavaScript. I don't know, like a JS object, maybe like some sort of thing, and then we call some free of X, but we still have X in JavaScript, which means that's very powerful, and that's one of the reasons that browser exploitation is so much easier than like server-side stuff. You have this X still there, and you can like rewrite its variables, you can call functions on it, you can do stuff like that. And X points to the stale in memory. So if we replace it with something, that's what use up to free generally is find out what we're gonna replace it with. I first triggered the bug like the line we saw before is F5 shitload and it fell over. And then I tried to replace this free memory, stale memory with something that I can control, and I chose strings because I can then put any values in there and I can play around with it. Normally I like to read the code and understand the vulnerability as best as I can. But then I ran into like all this crazy hash defined cycle stuff. I'm like, all right, fine, I just want to play around with values and see if I can just get a feel for it, see what other code parts are possibly available. So yeah, I defragmented the heap with particular size, allocated, and I triggered the bug. I closed the garbage collector and I allocated a bunch more of the size strings, so we overridden, also not overridden, but reallocated it at the top of, and I wait for the cycle code to kick in and see what happens. Really. It's very simple to do that kind of stuff. So we want to explore the various code paths that are available for this bug. The first one I chose the Vupin one because they had documented it, so it's less work for me. You can see here, this is actually the trace function for ID hearing. It's a fucking ugly as shit function. It's just like yelling at you with all these hash definings. So if you don't using Vim or something like that, you actually look at the stuff with the multi-line things, and that's hash defining multiple. Like his GC thing is like 4 levels of hash definings. So actually, when I first read the blog post, I was like, why the fuck are these people, just showing the assembly? It's for Firefox, they've got the source code. Why don't we put the source code? And then I dive in, like, oh, the assembly's clearer than the source. Gotcha. it's like, is there an object or a string there? And if it is, it goes and marks that. Or like goes and retrace that on that particular thing. It does that for an MPH low val and upper val, because these can be the two JS vals. And these are stored at offset 20 and 28 respectively inside the object, which is going to come into this later. So the first interaction, the boot interaction, this is a pseudocode. And so you have this pointer offset 20 because it's a JS val, and that's where the actual pointer is for the object. And you have that offset 24, the first one, you have like the object tag or the string tag. And they take that offset and they do some stuff to it, and they basically return with kindness and offset the data a number of these time values, and then using the switch statement, using more mapping stuff too. But essentially, what it boils down to is that we can order some data at a particular offset from a pointer that we give to them. And that's really powerful because we're providing there, it's not like a call, because calls are very difficult to give like a call pointer, because firstly we need to know where to call, so that's not, we need to turn this into some sort of info. So overrides can be much more powerful than a call. So Lupin did this with a heap spray, and they heap sprayed a bunch, and they managed to OR a length field in a string. And obviously then they have this very large string, which means they can read outside of the string's data, and then they can, it's an info leap, right? And they did, went from there. But I'm not going to do that because I'm on heap spraying. And the second interaction is this unlink. And once this object or fake object reference count reaches 1, and the traverse happens, it gets cleaned up by the cycle collector, which means it calls a bunch of functions in our object's V table. And this is very interesting because now we do have a call pointer we can control. But more importantly is that we can replace it with another object that has a 1 at its offset 4, and it has a V table at offset 0. The cycle collector is going to call a bunch of functions in the virtual table, and it's a completely different object to what is designed to be called. So we're calling a bunch of random functions, and hopefully we can maybe do something interesting from there.
Doesn't every object have a reference to itself? So the JavaScript would be something, right?
Yeah.
It's this reference.
So like
They're external, like all external references.
but not, we just need a 1 at that particular offset 4. Like it doesn't have to be a reference count, it just needs to be a number 1.
So different objects get reference count attributed at different locations.
Yeah, so they're generally at offset 4, but like, what if we have an object that doesn't even have a reference count? If we can make a 1 to be there, for whatever reason, then it'll go, hey, this is a reference count.
Right.
And go from there.
I think you got about 10.
10.
Minutes. Ish.
Okay. So I was a bit dumb at first. And I thought, I had this JS values there, why don't I replace them with other JS values? I don't know why I thought this was a good idea, but I did. It really doesn't have to get you anywhere. Well, firstly I thought, hey, if I maybe put like integers or booleans or something like that, maybe I'll take a different code path so they can't see from the source code because it's fucking ugly shit. So I'll just, whack them there. And I found out, doing this, that it ignores booleans and integers or anything that isn't a string or a bug, so there's like a pair on the tag type. And if we do put actual real objects there, all it does is it takes that pseudocode because they're real JS objects. It goes and all those values are actually legitimate places, and it marks it in the GC heap as this object is in use. So it just gets marked twice as in use because in OR the value is the same. So I basically got nowhere with that. Why I'm talking about it is that this is kind of useful for Firefox exploitation if you ever need to make so I need to make an array of JS values for a particular size that's smaller than the default when you reallocate from the GC heap to the JE malloc heap. You remember me saying before, when you reach 16, or I think 16 inclusive, or maybe 17 and above with an array object, the slots pointer is then allocated in the JE malloc heap. But when we do that, 16 or 17 JS values much larger than our OX38 object. So I was trying to figure out how can I make something that's OX38 sized and have it in the JE malloc heap. And I found that when you do function arguments, these are JS values, and they're immediately allocated in the JEML heap. So if you ever need to allocate JS values with a smaller number than what you normally do, you make a function and just essentially pass the values in here and do anything defragmenting like that. So yeah, but we need to work out how to replace it with legitimate objects, which will allow us these others to have two interactions. We can use this vtable being called, or we can create this fake JS value tag, which is something I'll go into in a second. But first we need to replace it with an object for a specific size. This like OX30 to OX40 non-inclusive. And it's a massive pain in the ass to find symbols that, or objects and classes that are a particular size. I don't know, kind of manually crazy. And you go with that list of DOM objects for IE is ADT presentation, which is also presentation. And you get like screenshots of either in there, like, you know, the side of either. I don't know how he did it, but like, if he did it manually for either, it's fucking insane. Maybe you use one of those like Argentinian, you know, slave labor exploit writers that they have to go through manually to do that. Well, you can also put like a breakpoint on the heap allocation functions, but then you've got the fuzzy problem where you have to have code coverage and actually you exercise the browser enough to create all these interesting objects, and then you have to then work out how to trigger them again. So that's kind of fun. So I wrote this tool called Simple Thingy because I call it Simple Thingy because I've never talked about it to people. It's basically a tool to search for sizes, for objects and classes of a particular size or between a range of sizes. And it parses PDBs, like the debugging file, using the common interface debugging interface access using Python because Python is the best. Yeah, so it's a very bare bones at the moment, but I need to work on it much more and then I'll release it. Yeah, I'm not going to go on GitHub because I'm an only child and I have problems sharing. Yes, this is simple thing as the name says. And I put a couple of DLLs in here. One's JS DLL, which is quite small in Zool. I was mostly working on Zool, but it's like 15 megabytes and my tool is shit ass and it like works. Like, it doesn't put anything in a database, it just works out every time, which means it's really fucking slow to search. But you only need to do a couple of searches. So you know, here's a class list of tons of different objects inside the thing, inside Moz.js. You can see here's our JS object and how it's actually changed very much over the course of a year or so.
How do you get the size?
It's just the symbol, the PDB tells you this is the size, and it's been reasonably accurate. There's been a couple where it's like, this is the size of the class, but also then I allocate some bunch of shit on the end for no reason, like, because it has other things. So, you know, you still have to go through it manually, but it's just good because, like, you know, I'm going to set, it's like 56 to like 68 or whatever. Also, you can also print out what's inside the class as well. So you can see here we've got this stack frame thing, and it's an offset 0, there's a unsetting flag, and offset 4, there's a union JS stack frame, whatever the hell that is. And this is what I use to go through to go and find objects that has a vtable and then has something that looks like I can possibly control it at offset 4, or it has a reference count at offset 4 to make it to this call. So yeah, I'll put that on my model.
So you're going to release that?
Yes.
Yeah, you're going to release the code to generate that, you're going to release all this stuff to generate it?
No, so it's actually like it's got an upload thing, so you just like upload your DLL to it and you can just search. Oh, this is divided into Django, and this is why my demos are all working.
So what do you think?
I haven't given it a go. It looks like ugly purple. So this quick JS file thing I touched on really briefly. So as I said earlier, this is 2 JS files at these particular offsets, 20 and 28. And this is in the legitimate object, right? And that means the tag is like 4 on from there, 24 on 2C. So if we can allocate an object over the top of that, and if there's an integer field there or something that we can control that's next to a pointer, let's say it's like we can control this mythical thing, we can then set this integer to be what the tag value is, and then when the trace thing happens, it goes, hey, there's actually a JS value here, instead of like a double or whatever it would be, and then tries to mark something into GCP, which is the boopin exploit with the boopin technique. But instead of us applying a pointer, object already has a legitimate pointer there, and would then mark something and offset from them. And I was like, hoping that I can find an object like this and set the value. You also set it to be minus or anything above A5, just as a compare, and then it doesn't jump below if not. It's the same as that, so you put like a -1 in there, and that would also take it to above. So yeah, it seems we could have done that. But unfortunately, I couldn't find any objects like this for this particular size that would allow me to do this. So I never really got much into how I could be, sculpting heat into it, or in something that I would like a length field. It's very annoying. Similar to the B table call, right? We were talking before, where we have offset 4, we have a 1 in there to do a call on these particular functions. I was hoping that we could replace an object with treated stuff. These functions do something interesting, which means read and write in, memory this should, because we don't control the arguments of these functions, and it's calling stuff and it's expecting that it has same arguments, but really it's setting up another function, really but it's getting different arguments. So I was hoping, read and write memories. I was hoping it would free itself, because if it called the destructor directly, it would decrement its reference count, and if the reference count then reached 0, it would get cleaned up, which means we could then do a use after free with a legitimate object. It doesn't have to have it vulnerability, but now we've freed it anyway because we've called this destructor. This stuff is very environmentally dependent, and I went through and I did manage to overwrite stuff and get stuff called, but every other function I did would either crash the program or wouldn't do anything. So like, where the fuck is my thing in this register in this piece app? So yeah, most probably these functions should not crash the program because that's a bit of a drag. Once again, I was not able to find any that fulfilled this particular criteria, so I got really desperate during that time. Yeah. At this particular offset in every process in Windows, there's this shared user data structure. It's like it's been there since XP, SP0, and it used to have some executable code that was then removed in SP2, Microsoft called Serious Web Security, and it's kind of like VDSO, and then it doesn't really matter what it is. But it has a number of function pointers to NTDLL offset, and I was like, hey, maybe I can call these functions because I know where they are in memory, and hopefully they'll do something. No, they did not do something useful. the nicest one I did get out of them was a clean exit. It was like, hey, you're doing some crazy shit, so I'm gonna fucking exit. So yeah, I was even being stupid by the time I tried to call the string in the end, and that obviously didn't. So I gave up. This is like last Thursday, and I worked on this for 3 weeks, and I'd gone to John McDonald, my boss, and much more time to take a crack at it, and he's just like, I can't come over, and you haven't come over, so it is potentially still possible. I mean, I was a bit fast and easy about going through some of the different classes. I'm pretty over this particular vulnerability. And it's most difficult because it's very limited interaction with a particular class. Like, we don't have a reference to it in JavaScript. The only reference still in there is this cycle collector, and there's only a couple of interactions that actually has with it. So it's not, it's limited scope. I think it's quite difficult for you want a heap spread. If you have any ideas, please hit me up in the bottom. Questions?
So then like 10 years of this, how did the version 3 spray thing work? They leaked address.
Is it leaked address? Do you mean they leaked something in it? I can't remember how they did the rest of their thing, because I read it a while ago.
That initialized variable in the GC, the object hasn't got cleaned up or called.
So they didn't know about the call technically. If they did that, it would be like they could have done one heap spray and then leaked, and then the normal trigger the bug again. But you don't need the heap spray to do it because these allocations are small. You just overwrite. You can just allocate over top of it again. And so they could have just done the call things. They know it wants JS or any of these other pointers. I can't remember. I probably should have. Heap sprays out. TLDR. I tried. I failed. But yeah.